So, welcome to our second lecture for this AP Biology course. Today we are going to take a brief venture into the biological macromolecules that serve as the building block for all living things. Now, you should have learned about these things in Bio 1, so I'm not going to cover in depth the basics of it. So I'll do a little refresher on the monomers. I'll look at their chemical structures. But the general principles about what each of these things do, you should already know. So I'm going to start this lecture off with talking about the backbone of all of the macromolecules, right? The backbone of all living things. Okay? And that is the element carbon. And now we refer to carbon as the backbone of life because carbon is found in all organic substances. Right? And organic molecules are molecules that we have deemed to be significant to living things. They fall under certain criteria. And so one of the criteria is that they must possess carbon. Now, not every molecule that possesses carbon is technically an organic molecule. Not even all of the molecules involved in life that possess carbon are technically organic molecules. An instance of that is carbon dioxide. Okay? Obviously, involved in living things, obviously has carbon in it, but it's not an organic molecule because it is not complex enough. Okay? So these organic molecules are also rather complex. Okay? So they vary in complexity. Right? The sugars are fairly simple. And the proteins are huge and ginormous and super complex. And so I'm going to start today by talking about some of the details of carbon. So, brief refresher on the basics of chemistry, right, of what makes atoms up. So all atoms are composed of subatomic particles. We have protons, which are positively charged. We have neutrons, which are neutral. And we have electrons, which are negatively charged. And now the protons and the neutrons have roughly equivalent mass. The electrons have an almost negligible mass. Right? It's like they don't weigh much at all. Okay? And so when we look at an element, we assess the element by how many protons it has. Okay? And we call the number of protons its atomic number. So carbon has 6 protons. The atomic number is 6. Okay? The carbon I've drawn on the board has 6 neutrons. Okay? So the proton mass plus the neutron mass, smush them together, you get the atomic mass. And for this carbon, it's 12. Now, some carbons have an extra neutron. Some carbons have an extra 2 neutrons. Right? And so if a carbon had 7 neutrons, its mass would be 13. Okay? If it had 2 extra neutrons, right, so it had 8 neutrons, the number would be 14. Okay? And so that's why if you look at the periodic table, carbon will have the atomic number of 6, but the atomic mass of 12.01 roughly, because they average in those forms of carbon that have more neutrons. But the carbon I have on the board has 6 protons, 6 neutrons, and 6 electrons. Because the number of electrons is the same as the number of protons, it's a neutral charge. And this is a standard carbon. This is the carbon that we deal with every day. Okay. And so the electrons exist in clouds. And clouds are a range of probability. So these electrons that we say are in the valence cloud, the outside cloud, right, you're most likely to find them in this range. And now this is not a two-dimensional thing. This whole thing is 3-dimensional, so this cloud extends out like a ball and around. So you got like layers, like an onion, right? And so elements are like Shrek, and Shrek is like onions. They got layers. And this outer layer has the electrons that can actually engage with the world, the ones that are going to be bonding and interacting with the other elements that are going to form the molecules. And now this second level valence shell is looking to have a total of 8 valence electrons. The default carbon has 4 valence electrons, indicating that we need to add a total of 4 electrons to this valence shell in order for this carbon to be satisfied. Okay. And we do that through covalent bonding. So, covalent bonding, as you should remember from chemistry, is when you have 2 separate elements sharing a pair of their electrons. So these shared electrons will join the overall valence cloud of both elements. And now it's not like a designated singular electron. Right? Basically, the 2 clouds merge and all the valence electrons are shared throughout this cloud. So that's a better reality of how electrons work rather than this simple 2-dimensional depiction. However, mechanically and functionally, when we look at the outcome, right, this 2-dimensional representation works. It's because it's like the carbon is sharing an individual electron with whatever element is next door. Right? And so, in order for carbon to be satisfied, it needs 4 more electrons. And therefore, it needs to form 4 bonds. It's going to share its electron with 4 other elements, and those 4 other elements are going to share its electrons back. And so now, overall, those shared electrons are going to satisfy the elements involved. So covalent bonds are very, very strong. They do require a bit of energy at the onset, like they won't just happen spontaneously. You do need to put a little bit of energy in, and they'll form. Okay. But once they're formed, they hold together very, very well. So carbon is looking for 4 friends. And it could be another carbon. It could be a hydrogen. Could be an oxygen. Or it could be a nitrogen. Could be a phosphorus, could be a sulfur. As long as we're building these biological molecules, it can be any of those organic elements. Right? Chunks, as you should recall, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur can all be involved. Now, the thing about carbon and its distribution of electrons and its valence shells construction, when it forms these 4 bonds, it leaves enough space in between its neighbors that the neighbors are not bumping into each other. You have to recall, you have to remember, keep in mind that these elements, these molecules, are 3-dimensional, real physical things. And it's easy to neglect the reality of their physical nature, because they're so tiny, tiny little tiny things. But if they get cramped and start bumping into each other and running out of space, they're not going to stay stable. And so in order to form a stable molecule, the different elements that are involved in the bonding have to have enough room around them to be comfortable. And the way that carbon is structured and the availability of its electrons make it so that everybody around it, all of its neighbors, have enough room to be comfortable. This 4 number of bonding is like ideal for bonding. Right? You can hold a lot of friends. You can hold 4 friends, which is a lot of friends. And all those friends have enough space to do their thing, right? And so if you're having a party and only one person comes to your party, that's no fun. Bad party. Right? You're having a party and 2,000 people come to your party. Oh, that's no fun. That's a bad party. In order to have a good party, you have to have just the right amount of people. And carbon is great at having parties. So, when we're talking about space between molecules, or rather, between the elements within a molecule, what we are talking about are bond angles, right? The angle between each of the connected molecules. And now, the closer that bond angle, or the smaller that bond angle, the more likely the electrons from this element are going to bounce into the electrons from this element. And that's not a very comfortable situation for either of them. Right? The electron's negative, and so there's that natural repulsion. Right? And so you get this strain within molecules if the things are too close, because they're trying to repel. Right? And so when you have these structures, the individual elements will kind of fall into place where they have the most room for themselves. Right? And so when you have a structure like this, you will find a uniform distance between these hydrogens. Whether I take this substance from New York or I take it from Milwaukee, right, they'll have that same bond angle because this gives each of these hydrogens the most space possible. Right? And now this bond angle is roughly 109 degrees. Okay? And that's a good amount of space for everybody involved. So here I got a cute little 3-dimensional version of this, right? And whatever way I rotate this, they're all going to have the same amount of space from one another. Right? And now this is particularly true because each of these points are hydrogen. And so they're all equivalent pieces. Now, say this edge was oxygen, right? And oxygen's a little bit bigger, so it might force these two hydrogens back a little bit, but it's still going to be roughly at 109 degrees, right? And so everybody's still going to have enough space to work, to live, to play happily. And so this property is what makes carbon such a fantastic backbone for all of the macromolecules. It offers up enough bonding space to really serve as a versatile bridge. But each of the molecule, or rather each of the elements that are stuck to that carbon, have enough room to be comfortable and to engage with other elements along the way. So the next useful thing about carbon in the story of organic molecules, organic stuffy stuffs, is its ability to form multi-bonds. And in this case, it's a double bond. Okay. Now, double bonds play a very large role in the way that these molecules function within living systems. Because double bonds change the way that these individual elements can move. When they're single bonds, they can spin and they can rotate and they move and they're flexible, right? So there's a lot of leeway, right? And so they can easily make space, and then somebody comes like, all right, I'm over here now, I'm up here, let me rotate back. Okay. With double bonds, however, that's not possible. Right? If you imagine you got a kiwi in one hand and a pineapple in the other, pineapple's too big. Let's change it to a clementine. You got a kiwi in one hand, you got a clementine in the other hand, right? You shove a toothpick in to the clementine, you jab that kiwi onto that toothpick, right? They can rotate freely around that one toothpick, right? Like they just spin on the toothpick. I could spin the kiwi all the way around while the clementine stays still. Right? You can imagine that, right? Here's my kiwi spinning, my clementine staying still. Okay. Now, you shove another toothpick in, and you shove the kiwi back on. Now you got 2 toothpicks, right? You can't twist the kiwi freely anymore, right? You have to rotate them together. Okay? And that's exactly the same thing that happens with double bonds. These two carbons are more strictly linked now, right? They're stuck together as if they had two toothpicks in them. So they can't freely rotate. So what this does to the structure of the molecule, in order to get as much space as possible, you'll have the carbon on this side go up and the carbon on this side go down, or vice versa. Either way, they'll be opposite one another. Right? And so this changes the amount of space that this molecule takes up. Right? You used to have something that would be just like that. Now you have something that's like that. Yeah? So it's taking up more space because it's not as flexible. Also important. So the next neato thing about carbon is that it readily forms these rings. Okay? And these carbon rings you see a lot in carbohydrates. When they take on these ring forms, they're very, very energetically stable. So these molecules are really hard to break unless you have the right chemical processes, which is important because these are the way that we store short-term energy, right? And so these carbon rings are are absolutely essential to the way that we operate as living creatures. And so carbon readily forms these rings. It's a nice closed circuit. The reason why they're so stable is because the electron distribution can be shared amongst all the carbons equally. Right? And so whenever you have an equal sharing of electrons, you're going to have a more stable molecule. Whenever you have one side that's a little bit more stressed than another, that's when you start getting unstable molecules, and the stress side is more likely just to pop off and leave, to make everybody more happy. But something like this, everybody's sharing the burden. And so this is a very, very solid structure. Okay? Great for storing energy. Okay? So we use this in our carbohydrates to store energy. Well, we don't, the plants do. And then we eat the plants and we take the sugars and we break them down for energy, right? When I say we, I mean all the living things. So that was my brief talk on carbon and its properties that allow it to function as the backbone for biological molecules, organic molecules. And the main takeaway is that carbon forms bonds in a way that allows for a significant number of groups to be attached to it without overcrowding those groups. Carbon itself is also rather neutral, and it's not electronegative, it's not trying to steal anything from the elements around it, it's not trying to push anything onto the elements around it, it's just trying to form nice, good old-fashioned covalent bonds with its friendly neighbors. And that's why carbon is the best backbone for biology. Thank you. I hope you've enjoyed this little talk. I hope you've enjoyed my classroom. I will see you again next time. Have a fantastic day.